Uh, Dear students, in this lecture, I'm going to talk about third order reaction. The reaction that follows third order kinetics. So far, we derived a rate constant expression for first order, second order uh, reactions. Now, I'm going to derive a rate constant expression for third order reaction. We say that reactant, this is, just imagine that this is consider this is an elementary reaction, a simple reaction. Three molecules of participating and giving product, and this follows third order kinetics. Let me write its rate expression. Rate equal to, right, in terms of reactant, I'll write decrease in decreases, reactant concentration decreases, so minus change in concentration of reactant with time equal to change in concentration of product with the time. This is how we define rate. This is equal to so you know rate constant will come and is directly proportional to concentration power 3 for a third order reaction. And as usual, say, okay, I'll write here A is converted into product is, let me say, time t0, at time 0 the reaction is not started. You have taken A mole per liter per decimeter cube of reactant. You have taken A mole and the product is 0. Product is not formed, so the reaction is not started. And after some time, let me assume T, x mole of product is formed. The unreacted molecule will be A minus x mole per liter. So at time t, so you substitute here, so rate equal to minus d at time t. At this time t, the concentration of reactant is A minus x by dt. So d concentration of product at this time, concentration of product is x equal to k concentration of reactant A at time t is A minus x power 3. So just this is rate equation. This is rate equation for this type of reaction. And for a third order reaction, this type of reaction is also possible. Three different molecules are involved. For this reaction also you can write rate expression. For this reaction, let me say at time t, at time 0, that the reaction yet to start, product formed is 0, reactant A is A mole, B is B mole, C is C mole. After some time t, x mole of product is formed. A minus x mole A will be remaining unreacted and B minus x, and this will be C minus x at time t. Now I'm going to write rate for this type of reaction. So rate, usual expression, minus dA by dt minus dB by dt minus dC by dt dP by dt. See, minus, so this it is plus equal to K concentration of A, N concentration of B, N concentration of C. So at time t, I know minus D, A is A minus x, concentration of A is A minus x by dt, and B, concentration of B is B minus X, concentration of C is minus D C minus X by dt. This is dx by dt equal to a rate constant into at time t concentration of A is A minus X, B is B minus X, and C is C minus X. Right, so for this reaction, this is your rate equation. For this third order reaction, this also follows third order kinetics, this also follows third order kinetics. For this is reaction, the rate equation is this, and for this reaction, rate equation is this. And also I can have one, and also I can have a reaction of this type, 2A reacting with B, and this product, this also can follow third order reaction. This type of reaction also can form third order reaction, can follow third order reaction. For this reaction also you can write rate expression, rate equation, right, like this. You can write rate equation, so I'm not going to write. If you integrate this rate equation, you will have rate constant expression K. But since many terms are involved, it will take some extra steps to integrate. This will be easy. Since in your syllabus only this is given, this type of reaction is given, so I'm going to integrate only this rate equation. And also I can derive this rate constant rate equation for this type of reactions also. Okay, anyway, I write, no problem. Say time t0, the product formed is 0. At initially I have taken B mole, initially I have taken A mole. At time t, X is formed, X mole of product is formed. How much B will be remaining? It's B minus X. How much A will be remaining? This unreacted A will be, it is not A minus X, it is A minus 2X. Because for every one molecule of B, 2 molecules of A is disappearing. So 1 molecule of B is disappearing, 1 molecule of product is formed. But 2 molecules of reactant A disappearing to form 1 molecule of product. So you have to subtract A minus 2X. This A minus 2X mole per liter will remain unreacted at time t. Just think of yourself. This is very simple. Okay, now I'm going to write the rate expression. Rate equation, rate equal to minus d A by dt equal to minus d B by dt equal to d P by dt. Here 2 molecules of A is involving, so as we defined, we have to divide it by 2. This is a mathematical form of rate. This is equal to K times A minus 2X and B minus X. This is rate equation for this type of reaction. So you have to integrate this equation to get the rate constant equation, or to get the expression for rate constant. So I'm not going to do it. I'll take a simple reaction. I'll take this simple reaction, and then I know it's rate equation expression. I'm going to integrate this equation. Okay, let me write that rate equal to minus dA by dt okay. Actually the expression, see, this is I supposed to write is 1 by 3. This is right expression for rate. So here also I would have written 1 by 3. This is the rate equation for this type of reaction. So this is minus 1 by 3 equal to dP by dt equal to K concentration of A power 3. So I'll take this equation, dx by dt equal to K A minus x power 3. Just integrate it. After rearranging it, integrate. This I can write this is integration x power n dx. This is x power n minus 1 by n minus 1. So this is a minus x minus 3 minus plus 1 plus 1 by n is minus 3 plus 1, and I have to differentiate this because this is not x, it is a minus x. So again I have to differentiate this with respect to x, and I have to write the result in the denominator. A is constant because initial concentration 0 minus x. If I differentiate with the x, I'll get 1. So this is K dt. If I integrate, becomes t plus I have to use integration constant c. So this is minus 2, this is minus 1. Therefore, minus 2 into minus 1 plus 2. This 1, this becomes, okay, let me write in the next step, a power minus 2 kt plus c. So therefore, 2 a minus x square equal to kt plus c. So as usual, we have to find out integration constant. So when time t equal to 0, I know x value will be 0. A x is 0, power 2, k t is 0 plus c. So c equal to 1 by 2 a square. So substitute c here in this equation, I'll get a minus x whole square equal to kt plus 1 by 2 a square, and rearrange this equation. Minus 2 a square equal to kt. 2 is common, so 1 by 2, 4 a minus x square minus 1 by a square equal to kt. So k equal to 1 by 2t 1 by a minus x square and minus 1 by a square is the rate constant expression for third order reaction, where only one only one reactant molecule involves. let me write this. I'll take LCM a minus x square into a square, cross multiplication a square minus a minus x square 1 by 2t. This is a square, this is a minus b whole square, right? So a square plus b square minus 2ab divided by a minus x square and a square, and the a square minus a square, you multiply minus sign, minus x square plus 2ax, a square minus a minus x square 1 by 2. This gets cancelled. I'll write 2ax minus x square by a square a minus x whole square. Okay, equal to 2t a square. X is common, right? I'll take x into 2a minus x divided by a minus x whole square. So this is all. This is another form of a rate constant expression, right? Okay, now half-life period expression, half-life period for third order reaction. I'll take this equation. Half-life period, I know half-life period when the product concentration must be half of the reactant concentration. So the reactant concentration should be uh, reduced to half of its initial amount. So I have taken a initial amount of the reactant, so it should become a by 2. Half of the amount of the reactant should be there. This is at half-life when time t equal to t of x equal to a by 2. I'm going to just I'm going to substitute here in this equation. Okay, equal to 1 by 2t. The t becomes t should be substituted with t of a minus x is a by 2 whole square minus 1 by a square. Just work out 2t of this is 1a, this is half a, becomes a by 2, this is a by 2 square, therefore 2 square by a square minus 1 by a square. This is 4, right? This is a, right? 2t of a 4 minus 1, right? Simple LCM k equal to 3 by t 2t of a square. So t of expression t of equal to 3 by 2k a square, right? So for a third order reaction, this is half-life period expression. You notice here that t of is inversely proportional to a square. This is the important observation for a third order reaction, that the square of the initial concentration, the half-life period of third order reaction is inversely proportional to square of the initial concentrations. This we observe. Okay.